So orthogonality principle is a very well-known principle used a lot in estimation theory. What it says is that the residual is always orthogonal to the optimal estimator. What I mean by that is um, if you use the x bar, right, to estimate the vector b, right, then the residual is going to be b minus x bar. This b minus x bar, or this r residual, this one, is going to be orthogonal to this ax, or is going to be orthogonal to this x bar, right? So x bar here, for the context of this linear equation that we are solving, we're solving ax equal to b. Let's take the best solution that we estimate is going to be the estimator. The best estimator is going to be ax hat, which is equal to x bar, right? So x bar is the best estimate of b. Then if you calculate b minus x bar or b minus ax hat, the residual that you get is going to be orthogonal to the optimal estimator. What was the estimator that we had? X bar, right? The estimator is x bar or ax, right? Okay, so what it says is that r is going to be orthogonal to x bar. Let's take a look at this diagram that I have to better understand this. We are trying to estimate this b, right? We are trying to estimate the b. Using what? What we get is x bar. This is the best estimate of b. When you subtract b from x bar, you get this r, this vector of residual. What it says is that this residual should be orthogonal to the x bar, right? So r should be orthogonal to x bar, which means that r should orthogonal to ax hat. Okay, very good. That's what it says. But now let's see why this is even correct. Why should this should be the case? Let's see. So we had this from the beginning videos that if A and B are orthogonal, then their dot product is 0. A transpose B is equal to 0. Okay, so let's find the dot product of AX bar and R. Let's see what we get. Remember, AX bar is a vector, right? So we write it as AX bar transpose times R. So instead of R, just plug in AX bar minus B. Okay, because that's what R is. And just transpose this one using the properties of transpose to be X bar transpose A transpose. Okay, let's multiply them together. We write this one as X transpose, X bar transpose, or X hat transpose. Then we get A transpose. We multiply A transpose by this. A X bar minus A transpose B. That's what I have here. But then wait, this one is 0. Why is that 0? This is just a normal equation. Isn't that just a normal equation? What was the normal equation that I had? The normal equation was A transpose AX is equal to A transpose B. But then if you move the right side to the left side, you get A transpose AX minus A transpose B equal to 0. That was a normal equation. Because our X hat is a solution of the normal equation. It's a solution of the least square, right? We are talking, this orthogonality principle is used in any estimation theory, mainly in MMSE, minimum mean square estimator, which least square is a class of MMSE, right? Or is a class of Bayesian estimator with a quadratic cost. Okay, right? It's similar to each other. Okay, now, so therefore, if this x hat is a solution of this one is gonna be 0. This is just a normal equation. So you see that ax hat and r are orthogonal to each other. Okay, very good. It's a very important property that the residual is orthogonal to the optimal estimator. Now let's talk about the least square, solving least square using the QR factorization. Okay, so what we're gonna do, we prove that the x hat, the solution of the system of linear equation, is gonna be a pseudo inverse times b. But from the couple of videos ago, when we talked about the inverse of matrix, I will put the link to in the description to these videos. Right? We proved that the left inverse of a matrix, or the left inverse of a tall matrices, or the square matrices, when we want to write it using QR, is going to be R inverse times Q transpose. Recall the way we get that. We had A transpose A inverse A transpose for the pseudo inverse, and all we do is just let A to be QR, and then you can obtain this, right? So in that case, X, the solution X hat, the solution is going to be R inverse Q transpose times B. So what do we do if you want to find the solution using the QR factorization? This is the step we follow. We are gonna first, let's see why this equation is correct. If X hat is equal to R inverse Q transpose B, go ahead and multiply both sides of this equation by R from the left side. So you're gonna get R X hat is equal to Q transpose B, and that's this equation. So here is the algorithm. First, compute Q transpose B, right? So first compute this Q transpose B. You can say that one can argue that first find the QR decomposition of A, but assume you have a QR decomposition of A, right? Assume we have already computed the QR decomposition of A. So once we have a QR decomposition, then calculate this quantity, Q transpose times B. Then find the X hat using the back substitution, since R is the upper diagonal matrix. Now let's talk about the least square for matrices. What I mean by that is when X is a matrix in a set of vector. So assume A is an n by n matrix, and now X is an n by k, since we have to, the dimension should match, right? And now we are seeking an X that minimizes the quantity AX minus B. The same expression, but now X is a matrix instead of vector. Okay? So if K is equal to 1, means that the X has only one column, then we get a normal least square. So if X is going to be like in a column vector, then we get a normal least square. But now what if K is greater than 1? Let's see what we get. So we only need to understand what happens when we have AX minus B square. Let me explain to you what happens. So in another video, we talk about the matrix multiplication. I will make sure to put a link to that video as well here. I said that when we have AX, where A is a matrix and X is a matrix as well, one way to interpret this is a column interpretation. You can write it like that, AX1. So X is gonna be this, with the columns x1, x2, all the way to xn. So ax1 is going to be the first column of ax, ax2. So you can just multiply a by different columns of x, all the way to ax. X is what's the dimension? N by k, axk, right? Good. Right, this is going to be the first column of ax, second column, and all the way to kth column. Because ax is going to be what's going to be the dimension of ax. Ax is going to be n by k, so k columns. Okay. Now you're going to subtract the b. What is b? B is going to be a matrix that is n by k. But b also can be written based on the columns. So B is going to be b1, b2, all the way to bk. So if you do that, you're going to subtract the first column from the first column of b. So you get ax1 minus b1. Because the result now ax2 minus b2 and axk minus bk. Okay, so that's what we're gonna get. Let's say we get the matrix like this: ax1 minus b1, ax2 minus b2. This is the second column, all the way to the kth column is axk minus bk, right? But recall from the beginning videos, that the Frobenius norm of a matrix, if you want to calculate the norm of matrix, the Frobenius norm is sum of the square of all the elements in a matrix, right? So like this, I from j1 to n, aij square, or it can be written as a sum of the square of norm of each column of the matrix. Please go and watch that video if you have not already. J1 to n, right? Aj norm of each column, right? So This expression is going to be the norm of the first column square, norm of the second column, all the way to norm of the last column square. Now we want to solve this, but this is very easy because now x1 is a vector, is the first column of x, right? And A is a matrix, B1 also is a vector, the first column of B. So we have, in a sense, we actually convert the problem to K, the sum of K least square problem, ordinary OLS, ordinary least square problem, right? So here I explain it only further since HXI appears independently. Now we want to minimize this one, right? If you want to minimize this expression, now we are in business. Look at that. The first term, this AX1 minus B1, only depends on X1. If you want to minimize this one respect to X1, right, you don't need to care about X2 or all the way to Xk. You minimize this term separately respect to X1. This is going to be a normal least square problem. X2, the second term, only appears in one term. X2 is only appears in one term, right? Let me just choose a correct color here. X2 and all the way Xk also. So each term can be minimized separately or independent from the other terms, right? And that's what I said. So xi hat is equal to 8 pseudo inverse times bi, right? So that's what's going to happen. Now, so let's say if you take the solution, which is going to be the columns of a matrix X, x1 hat is going to be the solution for the first, this one, the square. X2 hat is going to be the solution for this one, right? And then X is going to be solution for this, right? Good. So the solution for this x1 hat is going to be a pseudo inverse b1. This is b1, this one. The solution for the second one is going to be a pseudo inverse b2, and the solution for the last one is a pseudo inverse bk, right? And again, recall from the properties of matrix product, what is this one equal to? We are multiplying a pseudo inverse by every single column of B. This is nothing but a pseudo inverse B, right? Very good. So that's how you find the least square estimate for the X. So X hat is going to be this. Very good. So here I have also more explanation about that, but this is pretty much what I just described. That the norm of a matrix is going to be the norm of each column, and then here I just write the solution explicitly, that x1 hat is going to be nothing but A transpose A inverse, A transpose B1. What is this one? Nothing but pseudo inverse. What is this one? Pseudo inverse. What is this one? It's just pseudo inverse, right? Very good. So here it's just, I wrote the solution explicitly. Okay. So now a little bit about this. I've created another video about the least square estimation, which is the more advanced version of this. It's for more advanced audience if they already know about MMSE, minimum mean square estimator, and the relationship between MMSE and the least square. In that video, I introduced 3 different methods to solve the least square problem, or least square fitting problem. I will put a link to that video in this description. It's for another video series I have for the estimation and detection, essential estimation techniques in machine learning and signal processing. I have also written an article in Medium. I will put a link to that article if you want to check out more advanced estimation technique, like a Bayesian estimator, which is going to be a class of estimators that both MMSE and the least square are going to be a special class of the Bayesian estimator. I will put a link to that article also in that the description. Okay, so that's it about this video. Thank you so much for listening.